volume on this. Okay, I think we'd like to get started. My name is Paul Siegel. Christine Larson and I are the co-conveners of this Bowie lecture. And I thought I would just say a quick word about what the nature of these lectures are. Each of the AGU sections has a named lecture named after a Bowie medalist, and the Geodesy section is named after Bowie, fittingly. And this is a distinguished lecture which gives us a chance to hear from someone who's made very significant contributions to a particular field in more depth than we would hear in a typical 10 to 15 minute session. So today we're very pleased to have Jim Davis from the Smithsonian Center for Astrophysics talk to us. Jim got his PhD with Erwin Shapiro at MIT. After a postdoc at the USGS, he went off to CFA. And today he's going to talk to us about GPS investigations of post-glacial crustal motions for mantle dynamics, sea level change, and paleoclimate studies. Jim.
I'm going to put this map up. I can turn on the view graph machine. So I can refer to places. This is where this research started. This is from a paper by Celsius, the same Celsius as for the thermometer. And this is a top of a rock in the southern Gulf of Bothnia in Sweden. And he had reports, or there were reports of, we would call them anecdotal evidence, that people used to catch seals when they used to bathe on the rocks, and then it became harder for the seals to perch, to get up on these rocks. And this is this seal rock that he heard of. And he actually talked to a fisherman who described to him, when he was 10 years old, the seals would sit here, and then when he was 20, they'd sit there, and now they can't even get up. And this is his sketch of this rock in Sweden. And what Celsius did was to make an etch at the sea level in that rock. So from now on, we can measure sea level more accurately. And this is what this rock looks like today. The etching that Celsius made is in 1731. I'm not sure if he actually crawled out there or not, but he had it made. And they made etches in 1831 and 1931. And this photograph was made by Martin Ekman. There's quite a lot of work on sea level in Scandinavia. I asked him, is there going to be a mark made in 2031? And because I thought this was something official, and he says, well, I don't know. Usually someone local just, rows out and makes a mark. And this is from where he lives, so he says he'll hope to make that mark even though he's 80 years old. I emailed, fine, I'll watch you on television, because I'll be pretty old then, too. But you can actually see these marks aren't really very equal, even. And Celsius was able to estimate the rate of sea level fall. And it wasn't too bad. For this area, he estimated something like 1.3 centimeters per year, which is, I don't know, maybe 50% wrong, but still pretty good order of magnitude, as we'd say. Of course, it was just from those marks. So this was a pretty obvious phenomenon back then. And it was very important, too. It was important economically because rocks would start popping up in the harbor when your ships came in, and they would sink ships if you didn't keep track of it. So many hundreds of years ago, the Scandinavians were very conscious of this. they didn't know what caused it, and there were a lot of different theories. I won't go into them. I planned to review the history, but it reads like the history of everything in geophysics, a lot of, wrong ideas. Someone finally hit on the idea that the sea level wasn't falling, that maybe the land was rising. But then they still didn't know what was causing that. And some people thought it was because the Earth was cooling, and oddly enough, other people thought it was because the Earth was heating. So they could explain the same phenomena with two different initial assumptions. But the thing that they didn't know about that was important for them were the ice ages. And once they realized that there were these ice ages, that there were these times in the past where the large areas had been covered with ice, they realized that this ice could push down on the Earth and load it down, and then when the ice is removed, you could have some return to equilibrium that took some time. And this would give a nice regional signature, because after all, it seemed only to be happening in a few places. And they realized that these were the places that were covered with ice. So it was very quick that they came to realize that this was going on. And I was surprised to see how early they had a really good picture of what was going on. This is a map made by a guy named De Geer, but he actually used a lot of other maps. This is Scandinavia up here, and this is actually Lake Bonneville. And then we have, I don't know why it's tucked into the Scandinavia slide. And then we have North America there. So very early on, and these are contours of uplift based on these beach strands that you can see everywhere. These look like that. That's from Jerry Mitrovica. So very early on, they kind of had a very good understanding of what was happening, but it didn't really have a physical basis, a good physical basis. They were looking mostly at elastic models. They understood that, but it wasn't until 1935 when Haskell, in a really important paper, established the kind of hydrodynamical basis for this that we'd all understand and agree upon today, whereupon when a load is removed, you have kind of viscous fluid flowing in the area that's recovering. And this is a pretty recent history of the understanding of glacial isostatic adjustment, the theory that brings us up to the early 90s, which is when we started our GPS project. And I won't go into the details of this. There are some, but the important features here are that a Green's function approach was quickly hit upon and developed, whereupon a viscoelastic Green's function, kind of following on Farrell's work in an elastic Green's function, was used. And this is a time-dependent Green's function. And this depends very critically on the viscosity profile of the mantle. So the reason it's important to understand then that we use this Green's function approach, that's where our sensitivity to viscosity comes from. You then convolve this Green's function with the load, which is the ice, the history of the ice as it mainly disappears, and that's where we get our sensitivity to the ice history. Let me just go into a little bit this Green's function approach. They said it describes not only the spatial response of the Earth, but it also gives a time dependence to the Earth. A normal mode approach is used, developed, I think, mainly by Peltier, wherein you adopt these normal modes, which are really basis sets, which are exponential, because the response seems to be roughly exponential. So it becomes a matter of figuring out what sets of decay times to use and what strengths that go with it. Now, what's important to understand is that it's not a simple problem even there, even once you go through and calculate your Green's functions, because the time-dependent load actually consists of two connected parts. And if you just heard the last talk in the previous section by Hans-Peter Plog, it's basically what he's talking about. One is the ice sheets, which are the obvious part of the load. But unfortunately, or maybe fortunately, depends what problem you're trying to work on, when the ice melts, it doesn't leave the Earth system. It actually flows onto the Earth and becomes part of the load itself. Now, it distributes itself on the Earth in such a way as to maintain, to follow the basic laws of gravity, so that it doesn't just instantaneously form this kind of purely spherical or even elliptical form, right? You have to take into account the changing gravitational attraction of the ice sheets themselves, as well as the response of the Earth. As the Earth changes shape, its gravity changes shape. So you have this very related problem to solve, the viscoelastic form of the sea level equation that Hans-Peter Plog talked about, wherein you try to solve for the sea level, but the sea level is actually affecting the load too. And I drew this up. I don't know if this will actually clarify or make it more complicated. This relatedness between the changes in the ice loads, the response of the Earth, and the sea level. These are all related problems. And the way I've drawn this is you start over here, and the ice load somewhere melts or grows or something, and that means that the water that's melted from the ice somehow becomes part of the load, and this induces crustal deformation, which is really an internal redistribution of mass, which itself disturbs the geopotential. Of course, the geopotential is disturbed directly just by the water relocating on the Earth. So you have to take into account these gravity changes, and then from there, you talk about the water responding, which itself then becomes part of the load, and you kind of iterate on this. And actually, the sea level equation is solved iteratively. So you actually have to, when you're doing this problem, the process is you have the viscoelastic Green's functions, you have the ice load, and then you try to find this self-consistent solution that gives you the sea level and the response of the Earth and everything all together. And so these problems are all related very closely, sea level and rebound. Now, this is what a calculation for Fenno Scandia might look like. On the left-hand side, we have, for a given model here, an ice model and Earth model. Earth model, of course, giving you the Green's function. Vertical uplift rate. You can see that this model and actually most models give you this kind of bullet shape, this elongated bullet shape that's shaped like the Fenno-Scandinavian Peninsula, not surprising because that's where the ice was, and with maximum amplitudes of like 10 or 12 millimeters per year. And then you have on the right-hand side, the the tangential, the horizontal motions, and you can see down here the scale at 1 millimeter a year. So these are almost 5 millimeters a year up north. And the fact that you have this very asymmetric distribution follows from the fact that your ice load is asymmetric, and also it melts asymmetrically, and I'll get to that. So here we have a situation where this part here is known at some level and has been for 100 years. It's not known what we would consider very accurately until, say, recently. Maybe some leveling data gave you relative deformations at something approaching the millimeter per year level. And the horizontal motions have never been measured up until, say, about the advent of space geodesy. Now, there were some sites, space geodetic sites in this area going back to the old Crustal Dynamics project days. However, they were very sparse. And our idea was to then have a dense network, which would give you a very dense distribution of, relatively dense, of horizontal motions. And the obvious thing for someone like me in Boston is to work in North America. And actually, most of the questions regarding this project in the early days were why aren't I working in North America? So I had to come up with this list of reasons, kind of after the fact. However, the more I thought about it, the more it made sense. One thing that I realized that really helps us in Scandinavia is that it is a relatively small area compared to, say, North America or Antarctica or even Greenland. It's a relatively small area. That means it's easy to get a higher site density for a given amount of money. And we all know that's important. And then finally, it had a smaller ice sheet to begin with. And we knew from the beginning that the ice model would be one of the difficulties we would have to deal with. Everyone was saying, well, there's nothing you can do about the problems with the ice model. You take the ice models as given, maybe you can get a few different ones and compare them, but you have to take that as a given and go for what you can learn about the mantle viscosity. So smaller ice sheet errors. Finally, in some tests we did, there was very good sensitivity in terms of estimating mantle viscosity profile from the three-dimensional velocities. From the beginning, we realized that this was a really important strength that geodesy, modern-day space geodesy, could give us, is these three-dimensional velocities. People had been thinking purely in terms of uplift. It's still mostly called post-glacial rebound, even though it's not rebounding everywhere. In many places it's subsiding due to this problem, and it kind of ignores the horizontal component. But as you'll see, the third, or the other two dimensions, the horizontal component, really gives you a lot of strength. Furthermore, we know that even though the velocities are smaller, a few millimeters per year, we know we can estimate those more accurately. We have these problems with the vertical, kind of an inherent problem with the geometry, as well as a lot of other problems with dealing with atmosphere and other delay problems. I'll talk about that a little later. Very importantly, there was a very long existing, as I discussed, long existing because they realized that they did have this problem, set of tide gauges. The first tide gauge was put in Stockholm Harbor in something like 1740 or something, maybe someone can remember. It's the second longest tide gauge network. And as I said, this problem is related, the problem of sea level and the problem of glacial isostatic adjustment. Let me just show you three sets of tide gauge data. These are annual means from three places. One is Rakan in the northern Gulf of Bothnia. One is Stockholm, which is kind of at that little bump. I'm having trouble orienting myself on this. And then finally Helsinki, which is kind of over there. So you can see these tide gauges really give you some what looked like fairly accurate information. I was discussing this just a second ago, and for being these low-tech pieces of equipment, I mean, some of these still use strip charts. You can really get a lot of information. But the problem, the reasons that they were becoming important was because it became kind of a social problem to try to estimate sea level rise now that we were starting to worry about climate change. I'm not, whether you think it's man-made or not, become an issue as to whether the sea level is rising, and if it's rising, how much. If you look at the estimates, they're all over the place and relative to the size. Anywhere from 0 to 3 millimeters per year of rise are floating around in the literature. And the problem, of course, is that the land is moving, and these tide gauges are attached to the land. So that post-glacial rebound becomes something you have to correct for. It's not your signal suddenly, it's your noise. And Scandinavia, which has this really long set of tide gauges, would be a perfect place to help settle this issue of how much the sea level is rising, except for the fact that its land is undergoing these rather large motions, 12 millimeters a year compared to, say, 2 millimeters per year which is kind of a typical sea level rise result. So you have to correct for it. But because the ice is located in that area, and because your ice model is one of the things that has errors that you have a hard time getting hold of, tide gauges, for, data that are obtained in areas that were previously covered by glaciers have the highest probability that those ice model errors will influence the tide gauge results. And actually, when you use, say, a model like ICE3G to correct the Fenno Scandia tide gauges, this is a plot of sea level rate from the tide gauges versus sea level rate predicted from the ICE3G model, and any vertical difference here would be the eustatic, say, change, or at least a regional change. The regional change you get was very small with ICE3G, so small as to be almost nothing. 0.6 millimeters per year, although depending on how you weight, you can get almost a positive change. And you can also see some systematic differences. So you do this kind of procedure. You say, I have this great tide gauge data set. It's dense and it's long, and it'll solve the world's problems. And then you realize you can't solve the world's problems because you don't have a good rebound model, not good enough. So if you could actually obtain data on the uplift, you could finally use this to correct the Fenno Scandia tide gauge set, kind of bring this into the brotherhood of, accepted tide gauge results, and presumably make a big impact. And the final reason that we chose Fenno Scandia, although it's kind of the first reason, has a very good space geodetic history, both in terms of groups that are working there and in measurements that had been made previously. And we actually had an ongoing collaboration, actually predated Tom Herring even. It goes back to Erwin Shapiro and Bernd Renning in the beginning of the days when they were trying to convince people that you could use VLBI to measure motions of the plates, which is how they put it at that time. And so we formed this group of people that finally became Project Befrost. And Befrost actually stands for something. It's a little tortured, I know, but Befrost is a word. Befrost is actually a word that means something, and I always get a lot of flack from Jerry Mitrovica because I have to explain it, because Befrost is a mythological thing. It was the rainbow to Valhalla. And as Hans-Georg Schernet explained to me, at the end of the rainbow there was some gold, and if you wanted, you could dig for gold. It sounds it's not quite like our pot of gold, but this is Icelandic. But they used to have the same religion. So I just put this up to prove that I didn't make up the word Befrost. It's there with the rainbow. So no more flack on that. And that's the network as it finally became. And it evolved over time. And originally we had proposed a set of something like 15 sites that we would occupy twice a year. And the Swedes really didn't want to go out twice a year. And we realized that we were really pushing the signal to noise problem. So we decided to look for ways to do it continuous. And what happened was the state agency for land surveying, the National Land Survey of Sweden, stepped in and said, well, that's funny, we're going to have a permanent network of GPS sites. We don't want to do science with them. They don't have to be millimeter level. We want to have the civilian positioning network. And so we said, well, that sounds good. We can work together. And that's how that happened. Because they did things like, they were able to do things as a state agency, as a national agency, that we could never do, which is build structures and get internet access and phone access to places that you wouldn't normally think of going. These are two of our sites, just so you can see them. And these pillars here are actually warmed. There's a thermostat, and so they don't go below a certain temperature in winter. So they all kind of look like this. And the Finns were doing something similar and decided I think mainly out of reasons of competitiveness, that they didn't want us, doing such a project without them doing such a project. So they joined. At the same time, the Norwegians had quite an extensive effort themselves, and I don't show these here because they've had some they've had some changes in the kind of purpose of their networks, and really in the last few years, I think the data are the type that are needed to do this. We saw a presentation earlier this fall by Oddgeir Christensen, who showed some of those data. So I think pretty soon the Norwegian data will be available also. These are the Finnish sites, and they look horrific in terms of what you want for a continuous GPS site, because they're so high. But that's how they chose to do them, because they're trying to get, Finland has a lot of trees and a lot of animals, and they're just trying to get them up there. Now, what's nice about these is that they are monitored. There's kind of an in-bar wire running down these masts, and they are monitored at quite accurate level. And they've never shown vertical motions, at least, of more than a few tenths of a millimeter a year. So we actually started doing this work in early '93, and we knew that we'd have to wait a long time to get results. So this is always a problem for geodesists. What do you do while you're waiting for the rate? If anyone's from a funding agency here, you should know a lot of stuff goes on in between the measurements. And basically, once we looked carefully at the theory, we realized that it would have to be improved to be made commensurate with the kinds of results that we were getting, that we were expected to get. And a number of changes during this time were made. One is that we developed a pseudospectral approach to put the theory for the horizontal motions on the same footing as that of the vertical, so that they're calculated in a very consistent way. Then a number of changes to the sea level theory were developed. And remember, when you're talking about the sea level theory, what you're really saying is this becomes part of the load. So it's not, when you think of the sea level theory, you're also talking about things that affect the motions of the crust. And several changes have been made. This is ongoing research by us and by others, and we expect these kinds of things to continue. But one of the types of changes that was made was shoreline evolution, actually allowing for the fact that you don't have these kind of continents that are like step functions, and allowing for the fact that as the sea level rises, it actually puts a load in a changing area. Something that Glenn Milne has called post-glacial water dumping actually accounts for the fact that as ice is melted here, it's filled in with water, but in a way that can't just be treated in the normal kind of small change approach. So basically, you have this whole area here that's infilling with water, and that's a big difference. You can see here the kind of change this makes. Here's an ice model for 3 different epochs. This is the Lambeck ice model for Fenno Scandia. This is the load, the ocean load. You can't see it probably, most of you, in meters. The red is about 450 meters maybe. And this is the old theory. And basically in the old theory, when the water rushed in, it was treated just as a small change to the sea level that was there before, even though there wasn't any sea level there. So actually accounting for this, because remember, it's an area that had been depressed, you get this ocean coming in, and it's actually filling to a very high depth in those locations. So as you can imagine, this will make a lot of changes when you're worried about looking at very high resolution. If you're interested in, well, what's the effect of this, in southern Africa, for instance, thousands of miles away, you probably won't be able to see these small changes. But when you're working with your sites that are right along the edge there, it's an important issue. And finally, a feedback effect that a number of different people have worked on with the Earth rotations, the perturbations to Earth rotations. As the sea level redistributes, it causes the moment of inertia to change, and that will change the rotation of the Earth, which itself feeds back and imparts an effect on sea level. And we're talking small values, but the thing is that they're very systematic. And we're, to be truthful, we're probably not at the level now where these are, critical. However, we will be probably at some time. These are the rotation-induced perturbations to horizontal rates. The main driver for this is the huge load in North America. So the effects tend to kind of rotate so they point towards North America, which in the lower part of North America is straight up towards the Laurentia ice sheet. So you can see we're talking about this is old and new here, and I think new is the shaded arrows. Old without the perturbations in the open arrows. So you can see these make like a few tenths of a millimeter per year effect, and in Fenno Scandia they kind of rotate you towards Laurentia. Again, a few tenths of a millimeter per year. Another area where improvements were going on in the kind of almost 7 years since we've been observing is to the ice model. Now, I won't go into how ice models are constructed, but there's really no unique way to discern, say, from sea level data or from geologic data, the ice model. So you make a number of inferences, and you wind up with a non-unique ice model. That's fine. The issue is how true is that? And for the first time now, with especially getting horizontal vectors, we'll be able to put kind of a truth test to these ice models. And this is an ice model that's developed just for Fenno Scandia by Lambeck and others. It's a very high-resolution model, and it uses a lot of geological data inside Scandinavia. And finally, a change that I already alluded to was the switchover, I shouldn't say switchover, but at least adopting in some problems when it's relevant, and it can help you, the continuous GPS technique. Now, Befrost was not the first permanent GPS network, but it was among the first. I think the first that at least wasn't set up just to do orbit work or reference frame work, I think was the PGGA, which was set up in the late 80s. So this concept of actually using continuous GPS to do deformation studies, which we kind of accept now, was new at the time. Before that, the only reason you'd want to put something out permanently was if you wanted to help constrain the orbits. Now, with all this work going on, we still had some time on our hands, believe it or not. So one of the things that we decided to do was to say, well, is there some kind of other data type that's like GPS that we can at least apply our theories to and see if this thing is going to work? And what we came up with was the tide gauge data set. Tide gauges give you the relative sea level, at least on the coastline, and you can treat that as kind of a relative uplift kind of observable. It's not uplift, but it's sea level. As I said, these are related, and you can calculate them correctly and relate them correctly. And we were doing this. We published a paper about inferring mantle viscosity from tide gauge data in Scandinavia, and we wanted to see whether, actually we wanted just to see if the code worked, and we did the same thing on North America, and we found a really, I thought was, well, it was a startling result. It's not that earth-shattering or anything, but with just what we found was that the east coast of North America was extremely sensitive to the lower mantle viscosity. The way we found that out was, again, in North America, we had this problem that it's undergoing post-glacial rebound. The vertical rates aren't so large there because it's outside of the, south of the main ice cover. Nevertheless, if you're looking at 2 millimeters a year, you have to correct for this. And people like Bruce Douglas had kind of, were the first to say, okay, let's take the rebound model, correct the tide gauge data, and see if we get something more consistent. And what he found was that on the East Coast, at least, unlike other places, you didn't get something very consistent. You got something where in the north you have a value that's something like 3 millimeters a year different than in the south. And he couldn't explain that readily. And you can almost look at this data set and say, oh, it looks like it might make a step here. It depends which of these tide gauges you accept and, how you cut off for length of tide gauge series. But it turned out when we kind of applied our software to this problem that this was a problem with the postglacial rebound model itself. And in doing an adjustment, you could get something that fit these data a lot better. This is the raw tide gauge data up here, and this is the model that had been used to correct with, which is kind of a standard model that people were using. And by doing a simple adjustment to actually you can adjust anything you want, but it's the lower mantle viscosity that wants to adjust. You can see you can fit these data a lot better. And the residual series, these are rates now plotted as a function of latitude. It's a little late to say that, but fit a lot better with a lot fewer geographic variations. You can still see some, and these may be related to this effect that Hans-Peter Plog discussed earlier. That is, we don't expect it to be flat. Depending on where the melting is coming from, you might expect some variation in apparent sea level. So this gave us, actually these were the models that were developed. They don't look that different here, but again, in terms of millimeter per year, it is significant. And this gave us a lot of hope for what we could do with the Fenno Scandia data set when it finally came along. And it's been a long time in coming, I must say, longer than we thought. And I think there have been several issues here. One is simply that we had some problems to deal with that we hadn't anticipated, the biggest one being snow. And it's not so much that we didn't know that it snowed in Fenno Scandia. Believe me. But what we didn't realize was how much it stuck to the radomes. And nature wasn't even nice enough to have it stick evenly. It sticks unevenly. So we made a number of changes to our radomes, which was a mistake. Once we started that experiment, we shouldn't have changed it. And especially it was a mistake because it never worked. And I finally realized that this wasn't going to work one day when I saw a stop sign, in the middle of winter. And on the side of this vertical slick metal thing was snow stuck to the side. I figured if we can't prevent snow from sticking there, we can't prevent it from anywhere. We might be able to rig up something where, we heat the radome or something like that, introducing its own problems. But we never were able to do that. And so we have, first of all, when snow does accumulate, we have these problems. The data just, well, you'll see, they don't look very good during those times. And second of all, we have these self-induced kind of offsets where there was no site motion, but we changed a radome, which kind of changed the delay effect of the radome, which we have interpreted simply as offsets, although they're really phase errors. And this is a plot of data through the solution I'll be showing is through May 2000, through the end of May 2000, showing the east, north, and up here, east, north, and up. And the scale here is minus 30 to 30 millimeters for the east and north, and minus 60 to 60 for the radial. And Umio, maybe I should put up the network slide, if I can find it in my pile, since you've all memorized where the Gulf of Bothnia and where the Gulf of Finland are. So Umio is pretty far north in the Gulf of Bothnia. And you can see the effects of these jumps. And this particular, I fit a line through here. That's not how we necessarily do our solutions. We do include some annual terms, and we also do some editing. But this is like the entire data set, and just with a simple fitting of offsets. You can see the effect, both the horizontal and the vertical. you kind of reconstruct the time series by taking out those offsets, here's what you get. And this is what continuous data sets look like. You can see, some low frequency noise and some annual terms and such. And this one happens to have not too large horizontal motions, but a large vertical motion. Here's a Finnish site where you can see the real problem with snow accumulation. Umeå doesn't have that problem because it's right on the coast, and that kind of moderates temperatures and keeps snow from accumulating. Still snows there. But here in the middle of, most northern Finland, can you see where Kuusamo is? Here you get snow accumulating, and you can really see what happens. You can see it almost every year, 97, 98. 99 wasn't too bad. 2000 was a really bad winter. And in our standard solutions, quote unquote, we leave out the data actually from February 2000. So we try to deal with these problems as best we can. Like I said, some of them are self-induced. This is what our solution looks like, and this is from a paper that Glenn Milne has submitted to Science. What we show on the left are contours of uplift measured at the sites and then using GMT to fit a surface through. This surface fitting procedure gives us certain artifacts. For instance, you can see here in the north, you can see these funny-looking things. That's just part of this pattern, this oval pattern that GMT is fit that certain way. But you can see the same kind of pattern there as we saw in the models earlier. If I could find it, I'd put it up, but I can't find it. But basically, this kind of oval bullseye pattern, kind of tilted northeast. In the horizontals as well, you can see this very striking pattern of horizontal motions away from the center of uplift. Very high vertical horizontal motions in the north, associated with the fact that the center of uplift is somewhere here, and so in a very short distance here, you go to a zero load, and that induces very large horizontal motions. In the south, they taper off more gradually. Both to see whether these things are making sense or not, and to try to assess how well we're actually doing those measurements, not going by the formal errors. We've plotted here the observed 3D rates, east, north, and radial, versus a model, the Lambeck model. That's actually been, what we do is we take, the Lambeck model, ICE model, is a Fenno Scandia, and it's a local model, which is good. That's the way you should develop ICE models, because it means you're working very hard within a region. But actually the effect of the glacier retreat and the rebound in North America affects us. We can't ignore that. We don't ignore that. We do a full global model. So what we do is we take the ICE3G model, clip out Scandinavia, put in Lambeck, and that's our combined model. So here we're comparing this to the model, and if our observations were perfect and the model was correct, all our observations would lie in these diagonal lines here. Now you can see a couple of things. First of all, there are differences between that model. Second of all, the scatter, the clustering of the points is pretty good. For instance, you can see in the north there's a systematic variation. However, they all seem to cluster really nicely. It's not as though they're just random. So that leads us to believe that that both there's correlation with the model, and yet there are systematic differences from the model. Now, of course, some of these systematic differences might be reference frame, associated with reference frame, especially the way they are offset. Now, it's not as though, this doesn't show every single point that we used in the solution. We used a number of sites that actually do fix the reference frame. So those would be clustered, very close to the line in essence, if that, because their model is zero and their residual velocity is close to zero. So those aren't shown. But one way of then assessing the accuracy, it's a very crude way, and a very, if you will, it gives a very, say, an overestimate of the error, which simply you adopt a linear error model for the model, or for the data, but really for the model, and fit a line through it and determine the RMS fit. Those RMS fits are shown up here, and the lines are shown here in solid, and you can see the RMS fits for east are 0.4 millimeters a year, north is 0.3, and vertical is 1.3. So it's kind of a combined RMS of the data noise and the fact that we're just fitting some simple linear error model. So in actuality, I think that, especially for the radial, our true errors, for reasons I can't go into, I don't have enough time here, are about half that, but that still makes them around a millimeter per year. So that's where we are, millimeter per year. And I think we can see differences, say, between the Finnish network and the Swedish network, only because the Finnish network's been online less time, and so it's kind of a combined thing. So now we're at the point where we can start doing some fun things with these data. And we've just barely started doing this. We've done kind of a rough pass at a number of different applications. One is our original goal of using these data to determine mantle viscosity through the sensitivity of the Green's function. And what we've done here is calculated from a range of models. We're using a simple two-layer mantle here, upper mantle and lower mantle. And for a range of upper mantle viscosities and lower mantle viscosities, these are contours of chi-squared. And in the top one, we use the radial data only. In the middle one, we use the horizontal data only. And in the bottom one, we combine them. So you can see kind of the regions of sensitivity that these various data types are sensitive to. And if things were perfect, these would have minima in exactly the same places. But they don't exactly, but they do probably within the limits of variability of the chi-squared. But you can see the horizontal especially, we have not too much sensitivity to lower mantle. We get that from the radial. So the combined still has some of these kind of sled effects here. But we wind up with upper mantle viscosity of about 0.8 times 10 to the 21 Pascal seconds, and lower mantle viscosity of around 8 to 10 times 10 to the 21 Pascal seconds. That's a contrast of about a factor of 10. Now, 10 years ago, people were still arguing from rebound data about whether there was an isoviscous mantle. Well, maybe not 10 years ago, but let's say 13 years ago. And, of course, the data from many other areas indicate that doesn't seem right, and things have been slow to coming. But as far as we can tell, all the geodetic data we've looked at, either the Befrost data or the tide gauge data, that we have a much larger contrast in mantle viscosity. Than none. This is the same kind of thing, except it's one-dimensional. This is using our best fit mantle viscosities, looking at how the chi-squared changes as you change the lithospheric thickness. And you can see that it's pretty shallow here. So we're kind of in this range, which is around 120. We also decided to compare the model that we get to kind of the classic McConnell-type relaxation spectrum. This shows the relaxation time as a function of spatial distance. It's shown here as spherical harmonic degree that McConnell first did in '68. And this is actually a recalculation of this by Jerry Mitrovica and others. So you can see the model implied by the Befrost data kind of is this green one here, and kind of just touches the 1 sigma. values for the relaxation spectrum, at least at the low spherical harmonic degrees. Of course, we're not really that sensitive to some of those, but to 10 we are. And finally, one of the original goals was to look at sea level. And here, maybe you can't see this in the back, I just took this from a figure. What I'm showing here is the apparent sea level rate from tide gauges. They've actually been corrected or adjusted a little bit for this geoid variation that you get when you get the redistribution of the load that Hans-Peter Plog also mentioned. So it's not exactly what you get from the tide gauges compared to the radial rate from GPS. So of course the land is rising, the sea level is falling. That's why you get this negative slope here. Now the dotted line here is what you get if there were no kind of mean sea level change throughout the Baltic. Just the only sea level change you observe is due to the land rising. You get this dotted line. And in fact, it's not a best fit line, but we solve for a line with the slope equals -1 and just allow for an offset. Has an offset of about 1.9 millimeters per year. And that's very close to some of the numbers that people like Bruce Douglas get for global sea level rise, and actually even close to the value that Hans-Peter Plog showed earlier with a more complicated analysis. Now, I think this shows really nicely that you can get very good vertical results. There was some discussion when we first started, would we be able to see anything at all in the vertical, or would it look like mush? And I think that this plot kind of puts that to rest. The RMS fit we get here is around 0.8 millimeters a year. And that says something not only about the GPS, but about tide gauges too. And I actually think that tide gauges, although, as I mentioned before, they're a very low-tech form of measurement, can tell us a lot about, about sea level, but at the millimeter per year level. So I think here we get a very nice result. Now, when I did this, I didn't even bother to actually try to connect the tide. We didn't connect the tide gauges geodetically with the GPS sites. They're located sometimes 10 kilometers away, 20 kilometers away, and we didn't try to connect them. We wanted the best GPS sites we could, so we didn't try to put them right at the tide gauge sites. As a result, you could do a slightly better job if you, given the leveling that exists between those. You can see here even some systematic differences, especially in these higher GPS rates. That may imply that there is actually a tilt to this, and that may be due to the fact that a lot of what's causing this is Greenland melting. And as Hans-Peter Plog showed in his last talk, that has a spatial signature. And finally, once you subtract off your best fit model, what you have left, presumably, says something about what's happening outside of what you can model with post-glacial rebound. Here we can look at the neotectonics of Scandinavia. Now, a number of kind of theories / observations have been put forward for neotectonic motion in Scandinavia, the most recent of which was in GRL, I think 1999, and said there was some kind of shearing going on here in the Gulf of Bothnia. We don't really see signs of any of that. We do see some systematic things, but they tend to happen, they tend to be mostly for these northern Finnish sites, northeastern Finnish sites. So those are the sites that have been observing the shortest and also have the most problems with snow. So I'm not ready to jump up and down yet. These are actually, I don't know how many of you are watching that intently, but these are negative residuals. If you realize that, you get a prize or something. Now, there's a number of other projects going on. I won't be able to show all of them. One of them is this East Coast GPS tide gauge project. Steve Neerum, Tony Van Dam, Jerry Mitrovica, and I also have been involved with. And Steve has gone through and instrumented a lot of the tide gauges that exist in North America, and these are very nice tide gauges. You get some very good accuracy when you look at the annual means. He's also put some inland, which I think is a good idea, because what we're really looking at, I didn't really say here, but really is mainly going on in the East Coast, same thing that we looked at earlier, is mainly the subsidence that's happening at the level of about 3 millimeters per year. Now with GPS, you can also get the horizontal motions, and those are smaller again. Those will be 1 or 2 millimeters a year, but that's doable with GPS. These are what Steve's tide gauge sites look like. They're all a little different, but here you can see a tide gauge instrumented with the GPS receiver. Now, for his thesis, Kwandon Park has done the same kind of search, chi-squared search for mantle viscosity that we did with the Befrost data, and I'm pretty impressed with the results that he was able to get after only a short time. Now, he's plotted things sideways, I shouldn't say backwards, or just different than I have, DC term, differently to me. And he's plotted lower mantle this way and upper mantle this way. You can see that there's not much sensitivity to upper mantle, but this tremendous sensitivity to lower mantle that I talked about before when I said that we were able to estimate very accurately the lower mantle viscosity. And throughout all this, you finally come to numbers which are very close to the numbers we get with the Befrost results. This was given to me by Eric Ivins, and he's proposing a project in Patagonia. There's kind of ongoing melting there, but you get some very interesting patterns. I believe there are some GPS measurements from there. The Plate Boundary Observatory, I think, will be really useful in addressing some of these problems. As we discussed in the previous session, in North America, you have this tremendously large ice sheet, and that means that the deformations and the changes in the deformations occur well outside the area that was covered by ice, whereas in Scandinavia, they're pretty localized. So you can see that there still should be kind of measurable kind of strains down to almost northern Nevada. I don't know if they get quite to northern Nevada. I wish they did. But the plate boundary zone, I think, will help us fill in a lot. When I look for these now, when you look, it's just our GPS network now is too sparse. You need something that's more regular. This is the vertical motions, and you can see this kind of peripheral bulge, the area of subsidence. It actually gets big, kind of biggest, 3-4 millimeters a year, depending on what model you use, kind of in the plain states, or maybe here it shows it in Montana. Other models will give you, something that maximizes in Iowa. I thought about proposing a continuous network in Iowa, but given up. And finally, I wanted to get to some future work. I've talked only about Earth models and using GPS to estimate the Earth models. But in fact, we have a sensitivity to ice models too. The hard part is figuring out how do we parameterize those ice models. They vary in space and time, and there's so many degrees of freedom that it's hard to figure out how you can actually use the inferences of deformation to get at this. And this is something that we proposed and are working on, but I can't say that we've shown works yet, but I have high hopes for, where we actually use a finite element method to calculate the growth and the decay of glaciers. And those requires input climatological parameters and parameters in the physics of ice and things like that, parameters that we can estimate partial derivatives to, or calculate partial derivatives for, and then estimate corrections to. So I think this is the Befrost data set, I think, is a really rich data set. It's going to take time to kind of be plumbed, and I think there's a number of other projects ongoing. There's also one in Antarctica, and of course there's one in Canada. The Canadians have a network, and you saw Gene Sauber's results in Alaska. And so this is going to provide, I think, for a number of years, this very rich data set that can be looked at in a number of different ways, and that will that just take, right now, we're just at the beginning of. So that's all I have to say. Thank you.